Very good morning to all of you. Today I want to start session 4 of module 2. Title of the module 2 is Stress Distribution in Soils. Course outcome of module 2 is understanding of stress distribution and resulting settlement below the loaded footings on sand and clay soils. So this is the course outcome. Okay. Title of the subject is Applied Geotechnical Engineering and subject code is 18CV62 of 6 semesters. It comes in civil engineering departments. Contents. Today's session 4 contents are pressure bulb, pressure isobars for footings, contact pressure distribution in cohesionless soils. So these are the contents are prepared to explain in detail with respect to given loads to distribute the pressure into the foundations while applying the different type of loads, how these contents are behave. Okay, so that's today's class A. Now let us see pressure bulb. Pressure bulb is nothing but a electric current bulb concept of these diagrams. So this diagram is look like a electric bulb. Okay. See this diagram. This is the ground levels at a depth Z in meters. Acting load Q along the centroidal axis of the foundations, and these arrow marks are left side and right sides are located in terms of distance in meters from the centroidal points 0.1 meter, 0.2 meter, 0.3 meter, 0.4 like up to so on. And right side also distance in meter is considered 0.1 meter, 0.2 meter, 0.3 meter, 0.4 meter, etc. up to end of the footings. And here this is capital Q is the total structural loads. So due to structural loads at a depth of footings, how stress occurs in terms of pressure bulb. Let us see definition of an pressure bulb. An isobar is a line which connects all points of equal stress below the ground surface. An isobar is a line which connects all points of equal stress below the ground surface. In other words, an isobar is a stress contour. Isobar is a stress contour we may draw any number of isobars as shown in above figure 2.8. See these figures. So these are the different isobars. So these are the different isobars with respect to given load. See these are the different isobars. Okay. For any given load system, each isobar represents a friction of the load applied at the surface. Each isobar represents a friction of the load applied at the surface. Since these isobars from closed figures and resembles the form of a bulb, they are also termed a bulb pressure are simply the pressure bulb. Okay. An isobar is a stress contour or a line which connects all points below the ground surface at which the vertical pressure is the same. In fact, an isobar is a special curved surface and resembles a bulb in shape. This is because the vertical pressure at all points in a horizontal plane at equal radial distances from the load is the same. Thus, the stress isobar is also called the bulb of pressure or simply the pressure bulb. So, this is the definitions of isobar or bulb pressure. The vertical pressure at each point on the pressure bulb is the same. Normally, isobars are drawn for verticals, horizontal and shear stresses. The one that is important in the calculation of settlements of footings is the vertical pressure isobars. Okay, the one that is important in the calculation of settlements of footing is the vertical pressure isobars. Okay, pressure at points inside the bulb are greater than that at a point on the surface of the bulb. Okay, see here, according to this sentence, see this pressure, this is the contact surface and here pressure is more, stress is increased. Next, if load is increased, is second isobar is increased. If third you increase the load, third isobar is developed. Fourth structure is increased, fourth isobar is increased, like that at a certain depth. Okay, any number of pressure bulbs may be drawn for any applied loads, since each one corresponds to an arbitrarily chosen value of stress. Chosen value of stresses. A system of isobars indicates the decrease in stress intensity from the inner to the outer ones. Okay, a system of isobars indicates the decrease in stress intensity from the inner to the outer ones and reminds one of onion bulb. This is like a onion bulb. Hence the term pressure bulb. An isobar diagram consisting of a system of isobars appears somewhat as shown in figure above. See, this is figures. Okay, the procedure for plotting an isobar is, let it be required to plot an isobar for which sigma z equal to 0.1 times q per unit area, that is 10% isobars. Okay, assuming various values for z1, the corresponding kb values are computed. For these values of kb, the corresponding r by z values are obtained, and for the assumed values of z, r values are plots. Now I want to explain about pressure isobars for footings. Pressure isobars for footings. Okay. The following pressure isobars are given based on either Bosnisk or Westergaard equations. That is, Bosnisk isobar for square and long footings, that is shown in figure 2.9. Bosnisk isobar for circular footings, shown in figure 2.10. Westergaard isobars for square and long footings, that is isonic 2.11 means C. So these are the figures 2.9, 2.10, 2.11. See here. So this is the footing dimensions, okay, at a depth z in meters, or we are considering centroidal axis of the footings and distance we are taking left side and right sides is in terms of width of footings. Left side is 1b, 2b, 3b. Right side is also same 1b, 2b, 3b. And depth is also same, width is equal to the same depth, that is 1b, 2b, 3b, 4 times b, 5 times b. Here b is the width of the footings. Okay. We are considering breadth and the depth with respect to width of the footings, and we are applying the loads, that is continuous footings. So the square footings, continuous we are applying the loads. So then stress is occur like that. See first curve, second curve, third curve, fourth. So these curves with respect to depth, okay, at a 0.6 meter, 0.5 meter, 0.4 meter depth, 0.3 meter depth, 0.2, like that. So from the figure 9, this, if the stress, if the load is increased at a depth of the footings, so stress is also increased. Means 50% stress is developed left side and 50% stress is developed right sides in terms of semicircle concepts. See figure this, okay, 2.10 figure. See this is the ground levels and this is the structural load Q equal to 1000 kilonewtons applied, and you refer along the depth of the foundations at 1 meter depth, 2 meter depth, 3 meter depth, so on up to n number of in meters. So how stress is occurred? See here this shape of the curve. So this is the stress curve. At 1 meter depth, this type of stress is occurred. If more than 1 meter, if depth is increased, stress is occurred like that. Okay, so this line is called as isobar. This is vertical stress with respect to 400 kilonewtons. See this figure with respect to same. Okay, see if the load is increased continuous or uniformly distributed load is this, okay, such as load is occurred here along the width of the footing, that is in square footings. Okay, depth we are locating 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 meters up. Okay, and from the center line we are also considering equal distance 1 meter, 2 meter, 3 meter this sides, 1 meter, 2 meter, 3 meter this side with respect to centroidal axis, and we are seeing here shape of the stress diagrams. Now see the figure 2.11. See this figure. So this is the ground levels and this is the H depth, and the load is acting, that is surcharge load. This diagram is for circular footings of radius r. Okay, so with respect to depth of the footing, if stress is occurred like that, see this line is smooth curve, second is also smooth curve with respect to depth. If the depth of the foundation is considered in terms of 0.5 or 1 times of surcharge loads, so then how stress is happens, see from these diagrams. Okay, see these diagrams. So this is infinite strip. Okay, load is acted per unit area, that is Q, and see these are the depth of the footings. So we are considering this from here to here, depth is 0.5 times Q. Q is here surcharge load. Next x by 3, x by 10, x by 3. Here x is the distance, intervals. Okay, so while applying the surcharge load, stress is increased along the depth of the footings. So here Isobar is nothing but a contour lines. If the stress is increased, stress lines are increased in terms of semicircle curve nature, that is non-linear shape of the curve. Next topic is contact pressure. Next topic is contact pressure distributions. Contact pressure distribution. Theoretical distribution of contact pressure over the base of circular and strip footings. How contact pressures are developed. See with respect to applied loads. The term contact pressure indicates the normal stress at the surface of contact between a footing and the supporting earth. The term contact pressure indicates the normal stress at the surface of contact between a footing and the supporting earth. The problem of pressure distribution over the base of structure is of high practical importance, especially for flexible foundations which are to be calculated for bending. Okay. The upward pressure due to soil on the underside of the footing is termed contact pressure. This is one more definition. In the derivations of the preceding sections, it has been assumed that the footing is flexible and the contact pressure distribution is uniform and equal to Q. Actual footings are not flexible as assumed. Actual footings are not flexible as assumed. The actual distribution of the point at the surface, the contact pressure depends upon a number of factors such as the elastic properties of the footing material and soil. Elastic properties of the footing material and soil. The thickness of the footings. In fact, it is a soil structure interaction problems. For an elastic footing, the distribution of contact pressure depends on the elastic properties of the supporting medium, on the depth of the elastic layer, on the flexural rigidity of the footing, and on the distribution of loads on the footing. So these are the factors of contact pressure. Okay. See from this diagram, okay, how contact pressures are developed. See this figure, first one A, this is ground surface and this is footing dimensions, applied load Q. Okay. If the Q is applied, means structure is applied. So this diagram is in flexible footing on cohesionless soil at ground level. For flexible footings, if we are applying loads and we have designed flexible footings, so then how contact pressure is developed. So while increasing the loads, so pressure is developed like this shape of the diagrams. This is the for flexible footings contact pressure shape. See this diagrams second. This is for rigid footings. This is flexible footing. This is rigid footing on cohesionless soil at ground levels. Okay. So this is the ground level line. This is the footing dimensions. This is applied load Q in kilonewton per meter square. So if the load is applied, that is structural load for rigid footing, then shape of the contact pressure distribution diagram is like that. Straight, horizontal, straights. So this type of contact pressure is occurs, and these lines are upward pressure. So if the load is acting downward, then soil pressure is acting upwards in terms of frictions. This figure C, this is for mat or raft on cohesionless soils, mat footing or raft footings. Now how contact pressures are developed in terms of shape. See, here this is the smooth curve, but here this exit horizontals. Difference between this diagram and these diagrams. And this is figure D. So this is rigid footing on cohesionless soil below ground levels. Rigid footing below ground levels. Below ground level, if the structural load is occurred, so then contact pressure is occurred like that. If the below the footing. This is for flexible footing. This diagram is flexible footing on cohesive soils. So this is for cohesive soils. So all these are cohesionless. If the cohesive soil is open, so then here shape of the stress distribution diagram is occurred like that for flexible footing in cohesive soils. And this F diagram is for rigid footing. Is for rigid footing, okay, in cohesive soil. So shape of the stress distribution diagram is occurred like that, okay, straight horizontal states, and this is upward. So here this is concave and this is convex. So from the diagram, see here at the center stress is less, but at the corner stress is more. And this is convex, this is concave. This is the how contact pressures distribution developed in cohesionless and cohesive type of soils. Okay, and that contact pressure is also calculated in terms of equations. The relative rigidity is defined as Kr equal to 1 by 6 times 1 minus mu Vs square by 1 minus Vf square into Ef by Es times L by B cube. This is the equations. And with respect to the above diagrams, all the figure shows the contact pressure distribution of circular and stiff footings for different values of relative stiffness. For a perfectly rigid footings, Kr is considering as infinite. The contact pressure is minimum at the center with a value of about 0.5 times Q for the circular footing and 0.67 times Q for the stiff footings. The contact pressure is very large at the edges from the diagram. The contact pressure is very large at the edges. In fact, it tends to infinity. For purely flexible footings, the contact pressure is uniform and equal to Q. Contact pressure is uniform and equal to Q, that is applied structural loads. Borowick's results can be used to determine the contact pressure on a cohesive soil which behaves like an elastic soil mass. In a cohesionless soil, modulus of elasticity increases with the depth due to an increase in confining pressure. Such soils are non-homogeneous. If the footing is rigid, okay, I will explain once again. The settlement is uniform. The contact pressure distribution is minimum. At the center and the maximum at the edges. The stresses at the edges in real soils cannot be infinite as theoretically determined for an elastic mass. In real soils, beyond a certain limiting value of stress, the plastic flow occurs and the pressure becomes finite. Okay, and these diagrams are explained in details. Okay, and from this diagram, this is most important. Okay, this figures is most important. This figure shows the qualitative contact pressure distribution under flexible and rigid footings resting on a sandy soils and subjected to a uniformly distributed load Q. Uniformly distributed load Q. In this case, the edges of flexible footings undergo a larger settlements. See, the edges of the footings settlement is go largest settlements that at the centers. Okay, the soil at the center is confined and therefore has a high modulus of elasticity and defects less for the same contact pressures. Okay, the contact pressure is uniforms. These diagrams. Okay, so these are the diagrams are explains how contact pressures are occurs due to surcharge load, how its increase or decrease at the center or edges based on different type of footings. Okay, so these are the references are referred for session 4 with different textbooks, different IS codes, different journal, etc. studied in details for covering the session 4. Thank you one and all. Next class I will be continue.